Join me as I take on the challenge of explaining quantum computing in just 5 minutes. Quantum computing is a revolutionary technology that has the potential to transform industries and revolutionize the way we live and work. Understanding it is crucial for the future, as it's going to shape the next generation of technology and beyond. That's why it's essential to grasp the basics of quantum computing, even if you're not a tech expert. So, let's dive in and explore this fascinating world together. The impact of quantum computing will be felt across various sectors, from medicine to finance, and from cybersecurity to climate modeling. It's going to solve complex problems that are currently unsolvable with traditional computers. Imagine being able to create personalized medicines, crack complex encryption codes, or optimize complex systems with unprecedented accuracy. That's the power of quantum computing. But to appreciate the significance of quantum computing, we need to understand what came before it. We need to look at the history of computing and how it led to the development of quantum computers. That's what we'll explore in the next section. The history of computing is a fascinating story that spans centuries. From the earliest abacus to the modern supercomputers, we've come a long way. But it's quantum mechanics that laid the groundwork for the development of quantum computers. The principles of quantum mechanics, discovered in the early 20th century, changed our understanding of the universe and paved the way for the creation of quantum computers. In the early days of computing, scientists like Alan Turing and John von Neumann worked on developing the first electronic computers. They laid the foundation for the development of classical computers, which are the computers we use today. But it was the discovery of quantum mechanics that showed us that there's a different way to compute, a way that's more powerful and efficient. Classical computers use bits to store and process information, but quantum computers use qubits. Qubits are the fundamental units of quantum information, and they're what make quantum computers so powerful. In the next section, we'll explore the principles of quantum computing and how they differ from classical computing. So, what makes quantum computing so unique? It's the ability to exist in multiple states at the same time. This means that a qubit can be a 0, a 1, or both at the same time, whereas a classical bit can only be a 0 or a 1. This property, known as superposition, allows quantum computers to process vast amounts of information simultaneously. Another key principle of quantum computing is entanglement. When two qubits are entangled, their properties become connected, even if they're separated by vast distances. This means that what happens to one qubit instantly affects the other, regardless of the distance between them. It's a phenomenon that's difficult to understand, but it's what gives quantum computers their incredible power. Superposition and entanglement are the building blocks of quantum computing. They allow quantum computers to perform calculations that are beyond the capabilities of classical computers. But how do these principles work in practice? Let's take a closer look. Imagine you have a combination lock with 10 numbers. A classical computer would have to try each number sequentially to find the correct combination. A quantum computer, on the other hand, can try all 10 numbers simultaneously, thanks to superposition. This means that a quantum computer can find the correct combination much faster than a classical computer. Quantum computers also use entanglement to perform complex calculations. By entangling multiple qubits, a quantum computer can perform calculations that are exponentially faster than classical computers. This is why quantum computers have the potential to break complex encryption codes and solve complex problems that are currently unsolvable. But there's a catch. Quantum computers are prone to errors, and these errors can be devastating. The fragile nature of qubits makes them prone to decoherence, which means that they can lose their quantum properties and behave like classical bits. This is one of the biggest challenges in building a reliable quantum computer. Another challenge is scalability. Currently, most quantum computers are small-scale and can only perform a limited number of calculations. To build a large-scale quantum computer, we need to find a way to scale up the technology while maintaining its quantum properties. The race to achieve quantum supremacy is on, with tech giants like Google, IBM, and Microsoft competing to build the first practical quantum computer. Each of these companies is taking a different approach, from using superconducting qubits to topological qubits. The goal is to build a quantum computer that can perform calculations that are beyond the capabilities of classical computers. Despite the challenges, researchers are making rapid progress in quantum computing. They're developing new technologies and techniques to overcome the existing challenges. For example, some researchers are working on developing quantum error correction codes to mitigate the effects of decoherence. Other researchers are exploring new architectures for building quantum computers. They're looking at ways to integrate quantum computers with classical computers to create hybrid systems that can take advantage of the strengths of both. The potential applications of quantum computing are vast and varied. From optimizing complex systems to cracking complex encryption codes, quantum computers have the potential to transform industries. They can help us develop new medicines, create new materials, and solve complex problems that are currently unsolvable. Quantum computing has the potential to shape the future of technology and beyond. It's a revolutionary technology that can transform industries and solve complex problems. That's why it's essential to understand the basics of quantum computing and stay up to date with the latest developments in this field.